terms of reaction engineering, principles of chemical engineering ensures that the esterification process between acetic acid and ethanol reaches an equilibrium within the plant. By applying mass balance and energy balance, we can utilize these thermodynamic concepts to ensure the phase equilibrium when handling the reversible reactions within the reactants and the exothermic reactions that occur within the plant. With this method, we can ensure that the appropriate temperatures, pressure, and concentration of chemicals throughout the plant is constant. Principles of chemical engineering plays a huge role in the separation process within the distillation column. This distillation column will help purify the products. While using principles of chemical engineering, we can also maintain the safety and maintenance of the plant while also ensuring maximizing yields and minimizing byproducts.
Hello everyone, so I'll be explaining to you the calculation for mass balance in non-reactive system. Based on the flow rate diagram given, we can see that the feed rate given is 100 kg per hour, and the upstream is not given, but the downstream is given, which is 600 kg per hour. So in this case, there are a few steps that we can actually follow. The first step is define system input and output, which I have explained just now, the feed rate and also the downstream and also the upstream. And then we can convert the weight percentage to mass flow for each component. So in this case, some of the component is not given, but there are also some component that is given. So based on that information, we have to set up a mass balance equation and considering all in and all out equation. So in that case, we can find the mass flow for each component. And the last step is solve the system of equation based on all the equation that we have come up with. I'll be explaining the energy balance for non-reactive system. So based on the condenser flow rate diagram that is given to us, we can see that the feed rate is 100 mole per second, and also the upstream and the downstream is not given. However, each component molar flow rate is given, and we can see that from the feed rate there is a 66.9 mole percent of C3H8O, and which is in vapor form, and 33.1 mole percent of nitrogen in 25 degrees Celsius 1 atm, which is the reference state in this case. And for the upstream, 9.2 mole percent of ethyl acetate in vapor form is given, with 70 degrees Celsius and 1 atm as the reference state. For the downstream, 63.55% of ethyl acetate of the molar flow rate from the feed is given as an information. So in this case, when we want to find the ethyl acetate molar flow rate, we have to times 0. times the 63.55% to the feed rate to get the molar flow rate, and it is still 70 degrees Celsius in and 1 atm. So the step that we have to follow is first define the system input and output, which we have done just now, and calculate the molar flow rates based on all the information given, and consider all energy and all energy out. In this case, the only difference that differs from the feed stream and to the upstream is the temperature. So we have to use the formula that involves integration of Cp dt to find the specific enthalpy. And the fourth step is determine specific enthalpy of each stream, and lastly calculate energy change. Energy change are mostly in negative form, and we should get the answer in negative because it is energy change which shows the energy loss.
Determining the mass balance of reactive unit operation, the assumption given mass flow rate of acetic acid and ethanol fed to reactive vessel, ratio of acetic acid to ethanol 1:2, and efficiency of reaction 90%. And we need to determine the mass flow rate and molar flow rate for each product produced in reaction. Next, we need to determine the mass flow rate for inlet and outlet using the information given in the assumption. Then, from that information, we can calculate the molar flow rate for inlet and outlet by dividing the mass flow rate with their molecular weight for each component. And we put in the table and got all the molar flow rate for each component. Secondly, to determine the energy balance of reactive unit operation, the assumption given that the feed enter the reactor at 45 degrees Celsius and 1 atm and the products exit the reactor at 75 degrees Celsius and 1 atm. We can use the molar flow rate that we determine in mass balance calculation to determine the energy balance of reactive unit operation. To calculate heat of reaction, we need to determine the reference state for each component up to you all and prepare inlet-outlet enthalpy table for all the components involved in reaction. Next, we need to calculate the extent of reaction and standard heat of reaction because rate of enthalpy change are used to determine the heat of reaction. Also, we need to calculate specific enthalpies to all components involved in reaction. And the final step to calculate heat of reaction, we need to times all and plus all of the information that we calculate just now. And we got the final answer is 14711.96 kJ per second.
So fluid mechanics also impacts energy efficiency and sustainability. By optimizing flow rates and reduce pressure loss, engineers can minimize the energy needed to pump to the fluid. Additionally, designing piping networks, valve, and control system helps prevent pressure drops, which enhance efficiency, reduce maintenance costs, and prolongs equipment lifespan. Next will be the distillation column. The distillation column is a critical unit where fluid mechanics governs vapor-liquid interactions. These interactions enable the separations of ethyl acetate from water to others byproduct, which is essential to achieve high productivity purity. Next is the heat exchanger. The heat exchanger uses fluid flow principle to heat the reactant mixture to the desired temperature, ensuring optimal reaction rate while minimizing energy consumption.
This is our proposed design for our layout for the plant, and we have decided to use 6-inch Schedule 40 stainless steel pipes with an outlet diameter of 6 inch and inlet diameter of 6.5 inch. To make sure that our plant can support a high or higher flow rate, we have decided to use 6-inch diameter pipes with a Schedule 40 thickness. And to make sure that corrosion does not occur in the plant, we have decided to use stainless steel pipes. For the outlet diameter, we have chosen 6-inch and inlet diameter 6.5 inch for a large reflux and to ensure efficient flow and to prevent pressure drop.
Ethyl acetate is highly flammable and volatile component, so the delivery strategy for ethyl acetate are crucial. First of all, use strong, corrosion-resistant stainless steel pipes. 6-inch Schedule 40, which the outlet diameter is 4 inch and inlet diameter 6.5 inch. Next, 90-degree elbow fittings. Guide the flow safely and stop from dangerous vapor leaks. Other than that, to keep ethyl acetate cool and stable, use water cooling jacket to maintain the temperature at 25 degrees Celsius. It keeps ethyl acetate to evaporate since its boiling point at 77 degrees Celsius.
The formula that we are using is delta P equals to FD L over D rho V square over 2. So all the information that we will be using is stated in the slide. Next, for the calculation, first of all I find the velocity, which is 2.142 meter per second, and calculate the pressure for acetic acid and ethanol. And finally, I calculate the total pressure drop, which accumulated to 16554.49 Pascal.
So I'll be explaining how to estimate the pump power. Based on the information given, we have the dimension. The height is 7.12 meter, diameter in 50 meter, radius in 25 meter, and efficiency of 70%. We have to follow the formula for pump, which is the work actual is work ideal over efficiency. And also the power, the formula itself is molar flow rate times the work ideal that we have gotten over the efficiency. We have to assume that Q is 100 meter cube per hour. So from the Q that we have assumed, we can now calculate the mass flow rate, which is equals to density times Q, which is 100 times 0.02778, which is equals to 27.78 kilogram per second. And we will get the weight, the work ideal, which is equals to G times H, 9.87 times 7.12, and we will get 69.79 kilo per kilojoule. And now we can calculate the pump power, which is equivalent to mass flow rate that we have gotten and also the weight ideal that we have gotten over 0.7, which is the efficiency, and then we will get the answer of 2765.87 watt.
So now I will go over to the key features designed for our acetate storage tank to ensure it is safe, durable, and efficient. So first, let's talk about the material. The tank is made of 360L stainless steel because of its very resistance to corrosion, which is important for safety for storing acetic acid. We also use the PTFE gasket to prevent leakage and make sure all connections stay secured. So for the tank design, it's a cylindrical shape with a height of 7.12 meter and 50 meter diameter. The size is allow us to store enough sizes of acetic acid for the plant needed and make maintenance more easier. As for the temperature control, it is also very essential to keep the acid stable. So we use a water jet cooling system around the tank to maintain a safe temperature below acetic acid flash point, as well as the insulator planners to keep the temperature steady, and also the heating pads to be added in the cooler environment to prevent the acid from solidifying. As for the safety, we have a ventilation system and pressure release valve to control vapor. A nitrogen blanket is also used to create an inert, safe environment, and the tank is grounded to prevent static buildup. To prevent spill, there is a bund of wall that can hold 110% of the tank volume, and we also have a sensor to monitor levels, pressures, and leakage in real time, which help us to manage any issues immediately. Lastly, all pipe is made of 360L stainless steel with flector connection to minimize leaks and ensure its durability.